Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've been curious about how we came to understand the universe, or perhaps you're just looking for something to drift off to while learning about the brilliant minds who unlocked the secrets of reality itself. Either way, you're in the right place. Tonight's journey is a long one, spanning thousands of years from ancient stargazers to modern quantum physicists. And if these explorations help you unwind or give you something meaningful to fall asleep to, consider liking and subscribing to the channel. It helps others discover these journeys too. Now, let your mind relax, your breathing slow, and let's begin our voyage through the history of physics. The ancient roots of understanding. Long before physics had a name, humans looked up at the night sky and wondered. They noticed patterns in the movement of stars, tracked the phases of the moon, and watched the sun trace its path across the heavens. These weren't scientists in any modern sense, but they were observers, and observation is where all physics begins. In ancient Babylon, around 3,000 years ago, astronomers kept meticulous records of celestial events. They could predict lunar eclipses and understood the cycles of planets wandering among the fixed stars. They didn't know why these patterns existed, but they knew that they did, and that knowledge itself was powerful. The ancient Greeks took observation and added something new. They asked why. Around 500 BCE, in the bustling cities and academies of ancient Greece, philosophers began to propose that the universe operated according to principles that could be understood through reason. Thales of Miletus suggested that water was the fundamental substance of all things. Anaximander proposed that the Earth floated freely in space, held by nothing, an idea radical for its time. And Leucippus and his student Democritus put forward perhaps the most prescient idea of all, that all matter was made of tiny, indivisible particles they called atoms. They had no way to test this hypothesis, no microscopes or particle accelerators, but through pure reasoning, they arrived at a truth that would take more than 2,000 years to confirm. Aristotle, who lived around 350 BCE, attempted to create a comprehensive system to explain all of nature. He believed the Earth sat motionless at the center of the universe, surrounded by crystalline spheres that carried the moon, sun, planets, and stars in perfect circles. Everything on Earth, he said, was made of 4 elements: earth, water, air, and fire. Objects fell because Earth sought its natural place at the center of the cosmos. Fire rose because it sought the heavens. Motion, in Aristotle's view, required a continuous force. Stop pushing, and the motion would cease. For nearly 2 millennia, his ideas dominated Western thought, not because they were correct, but because they seemed to make sense of everyday experience and fit comfortably with philosophical and religious worldviews of the time. Then there was Archimedes, living in Syracuse around 250 BCE, who approached questions differently. Where Aristotle relied on pure reason and observation, Archimedes used mathematics. He discovered the principle of buoyancy, realizing that an object immersed in fluid experiences an upward force equal to the weight of the fluid it displaces. Legend says he discovered this while taking a bath and ran through the streets shouting "Eureka!" Whether or not that story is true What matters is that Archimedes understood that nature could be described with mathematical precision. He calculated the volumes of spheres and cylinders, found methods to determine centers of gravity, and even designed war machines based on principles of leverage and mechanics. He was, in many ways, the first mathematical physicist, showing that the physical world wasn't just something to wonder about. It was something you could measure, calculate, and predict. But after the fall of Rome, much of this knowledge faded in Europe, preserved mainly in the Islamic world where scholars translated Greek texts and made their own advances. Around 1021, the Islamic scholar Ibn al-Haytham, known in the West as Al-Hazen, wrote the Book of Optics, in which he described light as something that travels from objects into the eye, overturning the earlier Greek idea that vision involved light streaming out from the eyes themselves. He performed experiments with lenses and mirrors, studying reflection and refraction with a rigor that would not be matched in Europe for centuries. He understood that knowledge about nature had to be tested, not just reasoned into existence. In this way, he planted seeds that would eventually blossom into the scientific method. The dawn of the scientific revolution. For 1,000 years after Aristotle, his ideas remained largely unchallenged in European universities. Natural philosophy, as it was called, was subordinate to theology. The heavens were perfect and unchanging. The earth was the center of creation. To question these ideas was to question the order of the universe itself. But slowly, cracks began to appear in the old certainties. In 1543, a Polish astronomer named Nicholas Copernicus published a book proposing something radical. The sun, not the earth, was at the center of the cosmos. The planets, including Earth, orbited the sun in perfect circles. This heliocentric model wasn't entirely new. Greek astronomers had proposed it before, but Copernicus provided detailed mathematical models that could predict planetary positions more simply than the old Earth-centered system. His book, published just before his death, sparked controversy. If Earth wasn't the center of everything, what did that mean for humanity's place in creation? Religious authorities resisted, but the idea took root among scholars. Copernicus had shown that sometimes the universe doesn't care about what seems obvious or comfortable. Sometimes the truth requires you to see things from a completely different perspective. Decades later, in the late 1500s and early 1600s, a Danish nobleman named Tycho Brahe built elaborate observatories and measured the positions of stars and planets with unprecedented accuracy. He didn't have a telescope. That would come soon, but he had sharp eyes, carefully designed instruments, and obsessive dedication. After Tycho's death, his assistant Johannes Kepler inherited decades of observational data. Kepler believed in the Copernican model, but found that circular orbits didn't quite fit Tycho's measurements. After years of painstaking calculations, he made a breakthrough. The planets didn't move in circles. They moved in ellipses, with the sun at one focus. This was Kepler's first law of planetary motion, published in 1609. But Kepler didn't stop there. He found that planets moved faster when they were closer to the sun and slower when they were farther away, sweeping out equal areas in equal times. This was his second law. And finally, He discovered a mathematical relationship between a planet's orbital period and its distance from the Sun. These laws worked. They predicted planetary positions better than any system before. But Kepler didn't know why they worked. He had described how planets moved, but not what made them move that way. That question would fall to someone else. Around the same time, an Italian mathematician and astronomer named Galileo Galilei was turning a new invention, the telescope, toward the heavens. What he saw changed everything. The moon wasn't a perfect sphere. It had mountains and craters. Jupiter had moons orbiting it, proof that not everything revolved around Earth. Venus showed phases like the moon, evidence that it orbited the Sun. The Milky Way wasn't a glowing cloud, but a vast collection of individual stars. Suddenly, the universe was bigger, stranger, and more complex than anyone had imagined. But Galileo's most important contributions weren't just about astronomy. He performed experiments, something that Aristotle had rarely done. He rolled balls down inclined planes, timing their descent to understand acceleration. He discovered that objects fall at the same rate regardless of their weight, contradicting Aristotelian physics, which said heavier objects should fall faster. He studied pendulums and noticed that their period of swing depended on their length, not their mass or the size of the swing. He showed that motion didn't require a continuous force. Moving objects kept moving unless something stopped them. This idea, the principle of inertia, laid the groundwork for a revolution in understanding motion. Galileo didn't just observe nature. He questioned it, tested it, and showed that the physical world operated according to laws that could be uncovered through experiment and mathematics. For his efforts, particularly his support of the Copernican model, Galileo ran afoul of the Catholic Church. In 1633, he was tried by the Inquisition and forced to recant his views. He spent the rest of his life under house arrest, but his ideas couldn't be imprisoned. The old certainties were crumbling. A new way of understanding the world was emerging, one based not on ancient authority, but on observation, experiment, and reason. Newton and the birth of classical physics. In 1642, the same year Galileo died, Isaac Newton was born in a small manor house in rural England. As a young man, Newton studied at Cambridge, where he immersed himself in mathematics and natural philosophy. When the plague forced the university to close in 1665, Newton retreated to the countryside. Over the next 2 years, in what would become known as his Year of Wonders, he made discoveries that would transform science forever. Newton took the work of Galileo and Kepler and unified it into something far more profound. He realized that the force that made apples fall from trees was the same force that kept the moon in orbit around Earth and the planets in orbit around the Sun. This force, gravity, was universal. It acted between any two masses, attracting them with a strength that depended on their masses and the distance between them. Specifically, the force was proportional to the product of the masses and inversely proportional to the square of the distance. With this single equation, Newton could explain Kepler's laws, the motion of projectiles, the tides, and countless other phenomena. But Newton went further. He formulated 3 laws of motion that would become the foundation of classical mechanics. The first law stated that an object at rest stays at rest, and an object in motion stays in motion at constant velocity, unless acted upon by a net external force. This was Galileo's principle of inertia, made precise. The second law said that force equals mass times acceleration, providing a mathematical relationship between force, mass, and motion. The third law declared that for every action, there is an equal and opposite reaction. These laws weren't just descriptions, they were tools that could be used to analyze any mechanical system, from falling apples to colliding planets. Newton published his findings in 1687 in a book called Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy. The Principia was a towering achievement. Using his laws of motion and universal gravitation, Newton explained the motion of the planets with mathematical precision. He showed that tides resulted from the gravitational pull of the moon and sun. He explained why the Earth bulges at the equator and is slightly flattened at the poles. He demonstrated that comets weren't omens or supernatural phenomena, but natural objects moving in elliptical or parabolic orbits governed by the same laws as everything else. To perform these calculations, Newton invented new mathematics. He and the German mathematician Gottfried Wilhelm Leibniz independently developed calculus, a set of mathematical tools for dealing with rates of change and areas under curves. Calculus allowed physicists to describe motion, forces, and change with unprecedented precision. It became the language of physics, essential for expressing and solving equations about the natural world. Newton's universe was a clockwork. Everything moved according to precise, deterministic laws. If you knew the positions and velocities of all objects at one moment and understood the forces acting on them, you could, in principle, predict their future states forever. This mechanistic view was profoundly influential. It suggested that the universe was orderly and comprehensible, governed by laws that human reason could uncover. For the next 2 centuries, classical mechanics dominated physics. Scientists applied Newton's laws to an ever-widening array of problems, from the motion of fluids to the vibrations of strings to the orbits of newly discovered planets. The universe, it seemed, had revealed its deepest secrets. But even in Newton's time, not everything was understood. Light, for instance, was a mystery. Newton believed light was made of tiny particles, corpuscles that traveled in straight lines. But others, like the Dutch scientist Christian Huygens, argued that light was a wave, rippling through some invisible medium. Both views could explain some phenomena, but not others. The true nature of light would remain contentious for many years to come. The age of electricity and magnetism. While Newton's mechanics explained the motion of objects, it said nothing about electricity and magnetism, mysterious forces that ancient peoples had known about but didn't understand. The Greeks knew that rubbing amber could make it attract light objects, and they'd observed that certain rocks, called lodestones, could attract iron. But for centuries, these phenomena were curiosities, not subjects of systematic study. In the 18th century, that began to change. In 1752, Benjamin Franklin famously flew a kite during a thunderstorm, demonstrating that lightning was electrical in nature. He proposed that electricity came in two types, which he called positive and negative, and that opposite charges attracted while like charges repelled. Around the same time, researchers were building primitive electrical devices. The Leyden jar, invented in the 1740s, could store electric charge. Machines with spinning glass discs could generate static electricity. These weren't practical technologies yet, but they showed that electricity could be controlled and studied. In 1800, Alessandro Volta invented the voltaic pile, the first true battery. By stacking alternating discs of zinc and copper separated by paper soaked in salt water, Volta created a device that could produce a steady electric current. This was revolutionary. For the first time, scientists had a reliable source of electricity that didn't depend on friction or storms. They could experiment systematically, probing the properties of electric currents. Just a few decades later, the connection between electricity and magnetism began to emerge. In 1820, the Danish physicist Hans Christian Ørsted noticed something strange during a lecture demonstration. When he passed an electric current through a wire near a compass, the compass needle moved. The current was creating a magnetic field. This was the first direct evidence that electricity and magnetism were related. News of Ørsted's discovery spread quickly across Europe, and other scientists rushed to investigate. The French physicist André-Marie Ampère quickly developed mathematical laws describing how currents produce magnetic fields. Around the same time, Michael Faraday in England made a discovery that would change the world. In 1831, Faraday found that a changing magnetic field could induce an electric current in a wire. This phenomenon, called electromagnetic induction, is the principle behind electric generators and transformers. It's the reason we can transmit electricity over long distances and power our modern civilization. Faraday didn't think in terms of equations. He visualized fields, invisible lines of force filling space around magnets and electric charges. This was a radical idea at the time, but it would prove to be profoundly insightful. Then, in the 1860s, a Scottish physicist named James Clerk Maxwell took Faraday's ideas and cast them into mathematical form. Maxwell wrote down a set of 4 equations that unified electricity and magnetism into a single theory: electromagnetism. These equations described how electric and magnetic fields were created by charges and currents and how they influenced each other. But Maxwell's equations had a surprising implication. He found that oscillating electric and magnetic fields could propagate through space as waves, and when he calculated the speed of these waves, he got a number very close to the known speed of light. Maxwell realized that light itself was an electromagnetic wave. This was a stunning unification. Electricity, magnetism, and light, 3 seemingly different phenomena, were all aspects of the same thing. Maxwell's theory predicted that there should be other forms of electromagnetic radiation beyond visible light, waves with longer and shorter wavelengths. Over the following decades, researchers discovered radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, filling out the electromagnetic spectrum. Each type of radiation was just light of a different wavelength, all governed by Maxwell's elegant equations. Maxwell's work represented a peak of classical physics. Like Newton's mechanics, it was deterministic and precise. It described nature with mathematical beauty. But even as scientists celebrated these triumphs, strange cracks were beginning to show. There were phenomena that Maxwell's equations couldn't quite explain, mysteries that would require a complete rethinking of the foundations of physics. Thermodynamics and the statistical view. While Newton and Maxwell were describing forces and fields, other physicists in the 19th century were grappling with a more practical concern: energy. The Industrial Revolution was in full swing, powered by steam engines that turned heat into mechanical work. Engineers wanted to build better, more efficient engines, and this practical question led to deep theoretical insights. The study of heat and energy became known as thermodynamics. Researchers formulated laws describing how energy moved and transformed. The first law of thermodynamics stated that energy couldn't be created or destroyed, only converted from one form to another. The chemical energy in coal could become heat, which could become the kinetic energy of a moving piston, but the total amount of energy remained constant. This law of energy conservation was a powerful unifying principle, showing that different forms of energy were ultimately interchangeable. The second law of thermodynamics was more subtle and more profound. It stated that in any energy conversion, some energy always became unavailable for doing useful work. Heat flowed from hot to cold, never the reverse, without external input. Disorder, or entropy, always increased in isolated systems. This law had deep implications. It meant that processes had a direction in time. It explained why engines could never be perfectly efficient, and it hinted that the universe itself was running down, slowly moving toward a state of maximum entropy, a cold equilibrium where no further change was possible. But what was heat, really? For a long time, scientists had thought it was a fluid called caloric that flowed from hot objects to cold ones. But experiments in the early 1800s showed that heat could be generated through friction indefinitely, which didn't make sense if heat was a conserved substance. The English physicist James Joule demonstrated that mechanical work could be converted into heat with a fixed ratio, showing that heat was a form of energy, not a separate substance. The Austrian physicist Ludwig Boltzmann took this idea further. In the 1870s, he proposed that heat was really just the random motion of atoms and molecules. Temperature measured the average kinetic energy of these particles. When you heated a gas, you were speeding up its molecules. When you cooled it, they slowed down. This kinetic theory of gases explained not only heat, but also pressure, as gas molecules constantly collided with container walls. Boltzmann went even deeper. He connected entropy to probability. He realized that high-entropy states were simply the most probable states. If you opened a door between a hot room and a cold room, heat would flow from hot to cold, not because of some fundamental preference in nature, but because there were vastly more ways for energy to be spread evenly than concentrated in one place. The second law of thermodynamics wasn't an absolute law. Like Newton's laws, it was a statistical law, overwhelmingly likely but not strictly certain. This statistical approach was revolutionary. It suggested that beneath the smooth, deterministic world of classical physics lay a deeper reality of countless particles moving randomly. The macroscopic laws that seemed so absolute were really just averages, the collective behavior of unimaginable numbers of tiny entities. Most physicists were skeptical at first. Some, including the influential physicist Ernst Mach, didn't even believe atoms existed. They thought atoms were just a convenient fiction for making calculations. But Boltzmann persisted, developing his ideas with mathematical rigor. Ironically, the clearest evidence for atoms came not from thermodynamics, but from a seemingly unrelated phenomenon: Brownian motion. In 1827, the botanist Robert Brown noticed that pollen grains suspended in water jiggled around randomly. For decades, no one could explain this. Then, in 1905, a young patent clerk named Albert Einstein showed that Brownian motion could be explained if water was made of atoms constantly bombarding the pollen grains from all sides. He calculated how the pollen should move and derived a relationship that could be tested experimentally. When experiments confirmed Einstein's predictions, even the skeptics had to admit atoms were real. Boltzmann's statistical mechanics wasn't just a mathematical trick. It described something true about the underlying structure of matter. But by the time atoms were confirmed, physics was already in crisis. The seeds of that crisis had been planted in the 1890s, in experiments involving light, heat, and the nature of matter itself. The quantum revolution begins. At the end of the 19th century, physicists were feeling confident. Classical mechanics, electromagnetism, and thermodynamics seemed to explain the physical world. There were a few loose ends, but most expected them to be tied up soon. Then, in a series of shocking discoveries, the foundation of classical physics crumbled. One problem involved black body radiation. When you heat an object, it glows, first red, then white, then blue as it gets hotter. Physicists wanted to understand the spectrum of light emitted by hot objects. Using classical electromagnetism and statistical mechanics, they derived equations to predict this spectrum. But the equations gave absurd results. At short wavelengths, high frequencies, the predicted intensity shot up to infinity. Real objects obviously didn't emit infinite energy, so something was deeply wrong. In 1900, the German physicist Max Planck found a solution, but only by making a radical assumption. He proposed that energy wasn't continuous but came in discrete chunks, which he called quanta. The energy of a quantum was proportional to the frequency of the light. Energy equaled Planck's constant times frequency. By assuming that light was emitted and absorbed in these finite packets, Planck's formula perfectly matched experimental data. But Planck himself thought this was just a mathematical trick. He didn't believe energy was really quantized. He spent years trying to derive his formula using classical physics, but he never succeeded. 5 years later, Einstein took Planck's idea seriously. In 1905, a miraculous year in which he published several groundbreaking papers, Einstein explained the photoelectric effect using quantized light. When light shines on a metal surface, it can knock electrons loose, But experiments showed that the energy of these electrons depended on the frequency of the light, not its intensity. Bright red light couldn't eject electrons, but dim violet light could. This made no sense classically. But if light came in quantum packets, photons, each carrying energy proportional to frequency, then the result was obvious. A single high-frequency photon could give an electron enough energy to escape, while many low-frequency photons could not. Einstein's explanation was bold. He wasn't just saying that matter emitted or absorbed energy in quanta. He was saying that light itself was quantized. Light, which Maxwell had shown was a wave, also behaved like a particle. This wave-particle duality was deeply strange, contradicting centuries of thinking about the nature of light. But experimental evidence kept mounting. In 1923, the American physicist Arthur Compton observed that X-rays scattered off electrons like billiard balls, further confirming that light had particle-like properties. At the same time, the structure of the atom was becoming clearer. In 1911, Ernest Rutherford fired alpha particles at thin gold foil and found that most passed straight through, but a few bounced back at sharp angles. He concluded that atoms weren't solid spheres as previously thought, but mostly empty space with a tiny dense nucleus at the center. The nucleus contained almost all the atom's mass, while electrons, discovered in 1897 by J.J. Thomson, orbited around it. But this model had a fatal problem. According to classical electromagnetism, orbiting electrons should radiate energy as electromagnetic waves, spiraling into the nucleus in a fraction of a second. Atoms should collapse instantly. They didn't. Clearly, something about classical physics was wrong at atomic scales. In 1913, the Danish physicist Niels Bohr proposed a solution. He suggested that electrons could only orbit at certain specific distances from the nucleus, corresponding to specific energy levels. Electrons could jump between these levels by absorbing or emitting photons, but they couldn't exist in between. This explained why atoms emitted light at specific wavelengths, creating the sharp spectral lines observed in experiments. Bohr's model worked beautifully for hydrogen, the simplest atom. But it was ad hoc, a patchwork of classical ideas and quantum rules. It didn't explain why electrons had these special orbits or what an electron was doing while it jumped between levels. Bohr's model was a stepping stone, not a final theory. Then, in 1923, a French graduate student named Louis de Broglie had a wild idea. If light waves could behave like particles, could particles behave like waves? He proposed that electrons, and all matter, had a wavelength inversely proportional to their momentum. His thesis committee was skeptical. They asked Einstein's opinion. Einstein, who understood bold ideas, said the committee should give de Broglie his degree, that there might be something to it. A few years later, experiments confirmed that electrons could indeed produce interference patterns, just like waves of light. Matter had wave-like properties. The wave-particle duality wasn't just for light, it was universal. These discoveries shattered the foundations of classical physics. Matter and energy weren't behaving the way they were supposed to. The deterministic, mechanical universe of Newton was unraveling. physics needed a new framework, a new theory that could make sense of the quantum world. That theory would emerge in the mid-1920s in two different forms, developed almost simultaneously by two physicists with very different approaches. The birth of modern quantum mechanics. In the summer of 1925, a young German physicist named Werner Heisenberg was struggling with the problem of atomic spectra. Working at Niels Bohr's Institute in Copenhagen and later in Göttingen with Max Born, Heisenberg tried to build a new quantum theory from scratch. He made a radical decision. He would ignore any quantities that couldn't be directly measured. Classical physicists talked about electron orbits, but no one could see these orbits. What could be measured were the frequencies and intensities of spectral lines, the light atoms emitted and absorbed. Heisenberg built a mathematical framework around these observable quantities. He discovered that the quantities didn't behave like ordinary numbers. When you multiplied them, the order mattered. Multiplying a times b gave a different result than b times a. This non-commutative behavior was strange, but it worked. Heisenberg's approach could predict spectral lines with remarkable accuracy. When Heisenberg showed his work to Born, Born recognized something. Heisenberg's arrays of numbers were mathematical objects called matrices. Working with his assistant Pascual Jordan, Born developed this into a complete theory called matrix mechanics. It was abstract and mathematically difficult, but it gave precise answers to questions about atomic behavior. At almost exactly the same time, in late 1925 and early 1926, an Austrian physicist named Erwin Schrödinger was taking a completely different approach. Inspired by de Broglie's matter waves, Schrödinger sought an equation that described how these waves evolved in time. In a burst of creativity, he developed what became known as the Schrödinger equation. Instead of matrices, Schrödinger used familiar concepts from wave physics. His equation treated electrons as a wave spreading through space, and solving it gave energy levels and probabilities for where electrons might be found. Schrödinger's wave mechanics was more intuitive than Heisenberg's matrix mechanics, and many physicists preferred it. Schrödinger himself hoped it would eliminate the quantum jumps that Bohr and others talked about, providing a smooth, continuous picture of atomic processes. But this hope was dashed when Max Born provided a crucial interpretation. In 1926, Born proposed that Schrödinger's wave function didn't represent a physical wave. Instead, the square of the wave function's amplitude gave the probability of finding a particle at a particular location. Quantum mechanics wasn't predicting definite outcomes. It was predicting probabilities. This probabilistic nature was disturbing. It meant that even if you knew everything about a quantum system, you couldn't predict exactly what would happen, only the probabilities of different outcomes. Einstein was particularly troubled. He famously said, "God does not play dice with the universe." He believed there had to be some deeper deterministic layer beneath quantum mechanics. But as experiments continued to confirm quantum predictions, most physicists came to accept that probability wasn't just ignorance of hidden details. It was fundamental to nature. Schrödinger soon showed that his wave mechanics and Heisenberg's matrix mechanics were mathematically equivalent. They were two different ways of expressing the same underlying theory. But the two men disagreed on interpretation. Heisenberg accepted quantum jumps. Schrödinger found them abhorrent. These debates about the meaning of quantum mechanics would continue for decades. In 1927, Heisenberg introduced another concept that deepened the strangeness: the uncertainty principle. He showed that certain pairs of properties like position and momentum couldn't both be known precisely at the same time. The more accurately you measured a particle's position, the less you could know about its momentum, and vice versa. This wasn't a limitation of measurement technology. It was a fundamental feature of quantum reality. A particle didn't have a definite position and momentum simultaneously. Before measurement, it existed in a kind of limbo, described only by probabilities. Bohr developed a philosophical framework for understanding all this, which became known as the Copenhagen interpretation. According to this view, quantum mechanics didn't describe an objective reality existing independently of observation. Instead, it described what we could say about nature given the results of measurements. Properties like position and momentum weren't real until measured. The act of measurement brought them into being. The wave function represented our knowledge, not something physical. And different experimental setups, like measuring position versus momentum, revealed complementary aspects of reality that couldn't be captured simultaneously. This interpretation was deeply counterintuitive. Einstein, Schrödinger, and others never fully accepted it. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a thought experiment designed to show that quantum mechanics was incomplete. They imagined measuring one particle of an entangled pair and instantly knowing something about the other particle, no matter how far apart they were. This seemed to violate the principle that information couldn't travel faster than light. Einstein called it spooky action at a distance. He believed it showed that quantum mechanics was missing something, that there had to be hidden variables determining outcomes in advance. For decades, this debate seemed philosophical, not testable. But in the 1960s, the physicist John Bell showed that hidden variables would produce different statistical predictions than quantum mechanics. Experiments could decide. Over the following decades, numerous experiments tested Bell's inequalities, and the results consistently supported quantum mechanics. Entanglement was real. The universe really did exhibit these strange non-local correlations. Quantum mechanics, bizarre as it was, accurately described reality. By the 1930s, quantum mechanics had revolutionized physics. It explained atoms, molecules, chemical bonds, the structure of matter, and the properties of materials. It opened up new fields like nuclear physics and solid-state physics. It led to inventions like transistors, lasers, and eventually computers. It became one of the most successful theories in the history of science. And yet, even a century later, debates about its interpretation continue. Physicists still argue about what quantum mechanics really tells us about the nature of reality. Einstein's relativity and the fabric of spacetime. While quantum mechanics was revolutionizing the physics of the very small, Einstein was revolutionizing our understanding of space, time, and gravity. His theories of relativity, developed between 1905 and 1915, showed that the universe was stranger than anyone had imagined. In 1905, the same year he explained the photoelectric effect, Einstein published a paper on what became known as special relativity. The paper addressed a puzzle about the speed of light. Maxwell's equations predicted that electromagnetic waves traveled at a constant speed, about 300,000 kilometers per second, but constant relative to what? In everyday life, speeds add. If you throw a ball forward from a moving train, the ball moves faster relative to the ground than to the train. Light should work the same way, but experiments showed it didn't. The speed of light was the same for all observers, regardless of how they were moving. Einstein took this experimental result seriously and worked out its implications. He realized that if the speed of light was constant, then measurements of space and time couldn't be absolute. Different observers, moving at different speeds, would measure different lengths and different durations. Time could pass more slowly for one observer than another. This was a time dilation. A rapidly moving clock would tick more slowly, as seen by a stationary observer. Similarly, rapidly moving objects would appear contracted in the direction of motion, an effect called length contraction. These weren't illusions or tricks of perception. They were real consequences of how space and time worked. There was no universal now spanning the cosmos. Events that one observer saw as simultaneous, another observer might see happening at different times. Space and time weren't separate, absolute backdrops against which events played out. They were interwoven into a single entity, space-time. Special relativity had another famous consequence. Einstein showed that mass and energy were equivalent, related by the equation E equals mc squared, where c was the speed of light. A small amount of mass corresponded to an enormous amount of energy, since the speed of light squared was a huge number. This equation explained where the sun's energy came from. Nuclear reactions in its core converted tiny amounts of mass into vast amounts of light and heat. It also hinted at the terrible potential of nuclear weapons, which would be realized decades later. But special relativity only applied to observers moving at constant velocities. It didn't include acceleration or gravity. For the next 10 years, Einstein struggled to extend his theory. The result, published in 1915, was general relativity, one of the most beautiful and profound theories in all of physics. General relativity reimagined gravity not as a force, as Newton had described it, but as a curvature of space-time. Massive objects like stars and planets bent the fabric of space-time around them, and this curvature told other objects how to move. As the physicist John Wheeler later summarized, matter tells space-time how to curve, and curved space-time tells matter how to move. In this picture, the Earth orbits the Sun not because the Sun pulls on it with a gravitational force, but because the Sun curves space-time, and the Earth follows the straightest possible path through that curved geometry. General relativity made several predictions that differed from Newtonian gravity. Light, even though it had no mass, should be bent by gravitational fields. The orbit of Mercury, the innermost planet, should precess slightly differently than Newton's theory predicted, and in extreme situations, like near ultra-dense objects, space-time could be warped in bizarre ways. Some solutions to Einstein's equations even predicted the existence of black holes. regions where space-time was so warped that not even light could escape. In 1919, during a solar eclipse, astronomers measured the positions of stars near the sun's edge. General relativity predicted that the sun's gravity should bend starlight, making stars appear slightly displaced from their true positions. The coordinates measurements matched Einstein's predictions, not Newton's. News of this confirmation made Einstein a global celebrity. Here was a theory that not only explained gravity, but reshaped our understanding of space, time, and the cosmos. Over the following decades, general relativity passed every test. It explained the precession of Mercury's orbit. It predicted the existence of gravitational waves, ripples in space-time produced by accelerating masses, which were finally detected directly in 2010, a century after Einstein's theory. It described the expansion of the universe, discovered by Edwin Hubble in the 1920s. It even predicted its own limitations. Regions like the centers of black holes, or the initial moment of the Big Bang, where its equations broke down, hinting that a more complete theory was still needed. Nuclear physics and the heart of matter. As quantum mechanics and relativity were transforming theoretical physics, experimenters were probing deeper into the structure of matter. In 1896, Henri Becquerel accidentally discovered that uranium emitted mysterious rays that could expose photographic plates. Marie Curie and her husband Pierre studied these rays, which Marie named radioactivity. They discovered new radioactive elements like polonium and radium. Marie Curie's work was pioneering, and she became the first woman to win a Nobel Prize, and later the first person to win two. Researchers soon found that radioactivity came in three types, which they called alpha, beta, and gamma radiation. Alpha rays were helium nuclei, heavy and positively charged. Beta rays were electrons ejected from atomic nuclei. Gamma rays were high-energy photons. Radioactive atoms were unstable. Their nuclei spontaneously transformed, emitting radiation and changing into different elements. This was transmutation, the ancient alchemist's dream, happening naturally in certain atoms. Ernest Rutherford's 1911 discovery of the atomic nucleus suggested that an atom's positive charge and most of its mass were concentrated in a tiny core, but it wasn't clear what this nucleus was made of. In 1917, Rutherford discovered the proton, a positively charged particle that seemed to be a fundamental building block of nuclei. Hydrogen's nucleus was a single proton. Heavier elements had multiple protons, determining the element's identity. But protons alone couldn't account for atomic masses. Helium had 2 protons but 4 times the mass of hydrogen. Something else had to be in the nucleus. In 1932, James Chadwick discovered the neutron, a particle with about the same mass as a proton but no electric charge. Nuclei were made of protons and neutrons bound together by a new type of force, the strong nuclear force, which held them together despite the electromagnetic repulsion between positively charged protons. This understanding of the nucleus opened the door to nuclear physics and nuclear energy. Certain heavy nuclei, like uranium-235, could be split by neutron bombardment, releasing energy and more neutrons in a process called fission. These neutrons could split other nuclei, creating a chain reaction. This was the principle behind nuclear reactors and atomic bombs. In 1945, the terrible power of a nuclear fission was demonstrated when atomic bombs destroyed Hiroshima and Nagasaki, ending World War II and ushering in the nuclear age. Meanwhile, physicists realized that the sun and stars were powered by a different nuclear process: fusion. At the extreme temperatures and pressures in stellar cores, light nuclei like hydrogen fused into heavier elements like helium, releasing enormous energy. This solved a century-old mystery: where stars got their energy. It also explained the origin of the elements. Hydrogen and helium formed in the Big Bang, but heavier elements, from carbon to iron, were forged in the hearts of stars. Elements heavier than iron were created in supernova explosions. We are, quite literally, made of stardust. As physicists developed tools like particle accelerators to study nuclei and subatomic particles, they discovered that protons and neutrons weren't fundamental. They were made of even smaller particles called quarks, bound together by particles called gluons. They found other particles too. Electrons had heavier cousins called muons and taus. Neutrinos, elusive particles with almost no mass, zipped through matter almost undetected. A whole zoo of particles emerged, and physicists worked to organize them into a coherent framework. By the 1970s, they succeeded, developing the standard model of particle physics. This theory described three of the four fundamental forces: electromagnetism, the weak nuclear force responsible for certain types of radioactive decay, and the strong nuclear force binding quarks into protons and neutrons. The Standard Model predicted the existence of new particles, like the W and Z bosons and the Higgs boson, which were later discovered. It passed countless experimental tests with astonishing precision. But the Standard Model wasn't complete. It didn't include gravity. It couldn't explain dark matter, mysterious stuff that seemed to make up most of the universe's mass, but didn't emit light. It didn't account for dark energy, the strange force causing the universe's expansion to accelerate. And it left deep questions unanswered. Why were there three generations of particles? Why did particles have the masses they did? What happened at energies far higher than our accelerators could probe? Modern frontiers and lingering mysteries. Today, physics stands at a fascinating crossroads. We have two incredibly successful theories: quantum mechanics, describing the very small, and general relativity, describing the very large. Both have been tested extensively and never found wanting within their domains. But they're fundamentally incompatible. Quantum mechanics treats spacetime as a fixed background, while general relativity says spacetime is dynamic, curved by matter and energy. When physicists try to combine them to create a theory of quantum gravity, the math breaks down. One attempt at unification is string theory, which proposes that the fundamental constituents of reality aren't point-like particles but tiny, vibrating strings. Different vibration modes correspond to different particles. String theory naturally includes gravity and has the mathematical elegance that physicists find appealing. But it requires extra dimensions beyond the three of space and one of time that we experience. And so far, it hasn't made testable predictions that distinguish it from other theories. Another approach is loop quantum gravity, which tries to quantize space-time itself, suggesting that space and time are granular at the tiniest scales, made of discrete loops rather than being continuous. This approach is mathematically rigorous, but also hasn't been fully developed or experimentally tested. Then there are the cosmological mysteries. Observations show that ordinary matter, the stuff we're made of, accounts for only about 5% of the universe's total mass energy. About 27% is dark matter, which interacts gravitationally but doesn't emit light. We don't know what it's made of, despite decades of searching. About 68% is dark energy, an even stranger substance that seems to permeate empty space, pushing the universe to expand faster and faster. We don't understand its nature at all. And there's the mystery of the universe's beginning. General relativity suggests that the universe started in a Big Bang about 13.8 billion years ago, a moment when all matter, energy, space, and time emerged from an unimaginably hot, dense state. But what came before? What caused the Big Bang? Did time itself begin then, or is our universe part of a larger multiverse? Current physics can't answer these questions. Despite these gaps, the progress of physics over the past few centuries has been extraordinary. We've gone from ancient philosophers wondering about the stars to understanding the evolution of galaxies and the quantum behavior of atoms. We've harnessed nuclear energy, sent spacecraft beyond the solar system, and developed technologies like lasers, computers, and GPS that rely on quantum mechanics and relativity. We've peered back to moments after the Big Bang and detected gravitational waves from colliding black holes billions of light-years away. Physics has shown us that the universe is far stranger than common sense suggests. Time can slow down. Particles can be in multiple places at once. Empty space seethes with energy. And yet, despite this strangeness, nature follows laws that we can understand, express in mathematics, and use to make predictions. This is perhaps the deepest mystery of all. Why is the universe comprehensible? Why does mathematics, invented by human minds, describe physical reality with such uncanny precision? A gentle conclusion. And so, as you drift off, consider the long journey we've taken tonight. From ancient Greeks pondering atoms, to Galileo dropping weights from towers, to Newton unifying earth and sky, to Maxwell revealing that light is electromagnetic, to Planck, Einstein, Bohr, Heisenberg, and Schrödinger unraveling the quantum world, to Einstein bending space-time itself. Each generation built on the last, sometimes confirming, sometimes overturning what came before. The history of physics is a history of human curiosity and creativity, of asking why the universe works the way it does and refusing to accept easy answers. It's a history of thought experiments and careful measurements, of brilliant insights and stubborn puzzles, of theories that explain vast swaths of nature and mysteries that remain tantalizingly out of reach. You're part of this story. The atoms in your body were forged in stars. The same laws that govern distant galaxies govern the neurons firing in your brain. The universe has spent billions of years bringing you here, to this moment, drifting between waking and sleeping, between thought and rest. Physics hasn't answered every question. It may never answer every question. But it's shown us that the universe is a place of profound order and beautiful mystery. It's taught us that reality is richer and stranger than we ever imagined. And it's reminded us that we can understand it, piece by piece, if we're willing to observe carefully, think deeply, and remain open to having our certainties overturned. The stars still shine above, as they did for ancient astronomers. But now we know what they're made of, how they were born, and how they'll die. We know the universe is expanding, and we can trace its history back to the first fraction of a second. We know that space and time are woven together, that matter and energy are two sides of the same coin, that the act of observing can change what's observed. If you're still awake, I hope this journey gave you something to think about. And if you found this helpful, if these explorations into science gave you a peaceful way to end your day, please consider liking this video and subscribing to the Sleepy Science Society. It helps more people discover these gentle journeys through knowledge. Rest well tonight. Dream of falling through curved space-time. Dream of quantum waves lapping against the shores of probability. Dream of photons racing from distant stars, bringing light across billions of years. Dream of the universe, vast and strange and beautiful, unfolding according to laws we're only beginning to understand. Good night.